Okay, welcome back to the class. Yesterday in previous class, we have been discussing about the kinematics of plane motion of a rigid body. And while discussing the kinematics of plane motion of a rigid body, we understood that whenever a rigid body is in plane motion, as far as the motion of the plane body, when visualized by locating any 2 points on the rigid body, the 2 points, if we draw the vector between the 2 points, it was quite clear that the vector was having some amount of angular velocity associated with it. Let's try to understand again what we had done. Let's suppose we locate our coordinate system. Let's suppose we have a frame of reference, and the frame of reference is, let's suppose this we treat as our x-axis, and we treat this to be our y-axis. And let's suppose that we have the ground frame of reference from which we will be measuring the motion. Okay, let's suppose this is our ground frame of reference. In this ground frame of reference, we have this as our x-axis. This is the x-axis of our ground frame of reference. This is the y-axis of our ground frame of reference. So we mean to say that as far as this xy coordinate system is concerned, this xy coordinate system we have fixed in ground. From the ground, okay, which is from the ground frame of reference, we'll be observing the motion of some of a rigid body which is undergoing the planar motion. Let's locate 2 points of the rigid body. Let's call this as point P, and we have another point. Let's call this as point Q. Point P and point Q are the 2 points of the rigid body. Now let's draw the radius vectors. Let's say the point P of the rigid body is having a radius vector. This is the radius vector of point P, and the radius vector of point Q is, this is the radius vector of point Q, and we also have the radius vector between point P and point Q, and let's define that radius vector as, this is the radius vector between point P and point Q. So we initialize all these vectors as we say the radius vector drawn from O, the origin of our ground frame of reference to point P. Let's call this as, let's say this is radius vector drawn from point O to point P. We call this as ROP. In the same way, the radius vector drawn from point O, origin of the ground frame of reference, to point Q of the rigid body, let's call this as ROQ. And the radius vector drawn from point P to point Q, let's call this as RPQ. So we have 3 points. We have defined the radius vectors drawn from the ground frame of reference, origin of the ground frame of reference, to 2 points, point P and point Q of the rigid body. Now, as far as the angle is concerned, as far as the radius at this instant when we are just trying to understand the motion of the rigid body, let's suppose the angle that it subtends along with the x-axis, the angle that is being subtended with the x-axis, the radius vector, the RPQ, the angle subtended by the radius vector RPQ with x-axis, let's call that as, let's say that angle is theta, and this theta is a function of time, because we know as this body will describe some planar motion, the value of theta will change for different instants of time. The value of the theta will be different. That's why we write this as theta as a function of time. We also define since we are saying the frame of reference, this xy frame of reference is our ground frame of reference, we define the unit vector along x-axis as I cap. This is the unit vector drawn along x-axis as I cap, and we also define the unit vector drawn along y-axis, we define that as j cap. Okay, therefore now we can write from the from triangle law of vectors. From triangle law of vectors we can write, if you look at this diagram, ROP and RPQ are in the same sense. Okay, as far as ROQ is concerned, it's in the opposite sense. Therefore we know from the triangle law of vectors, I can write here from the triangle law of vectors, from triangle law of vectors we have from triangle law of vectors we can simply write ROQ vector, which is the position vector or the displacement vector of point Q as measured from the origin of the ground frame of reference. ROQ will be equal to ROP vector plus RPQ vector. Okay, this is from the triangle of vectors. And what we do, we call this as our equation 1. So this is our equation 1. Now, this equation, this RPQ, they are the radius vectors. Okay, ROP is the radius vector, ROQ is the radius vector. If we try to understand what does this ROQ give us, at a given instant of time, this ROQ gives us the position of point Q as measured from the ground frame of reference. So if we have the observer at ground, and at an instant of time we ask the ground observer where is the point Q, the observer will say that point Q is at a distance ROQ from me. Okay, so it will give us the direction of the point Q as measured from the observer at point O, as well as its direction. Okay, same is the case with point P. So now if we ask the observer at point O, if we ask the ground observer what is the velocity of point Q of the rigid body with respect to you, what is its velocity, please comment on the velocity of point Q. Then the observer at the ground will say that the velocity of point Q will be the derivative of this position vector. The derivative of position vector with respect to the person on the ground will be the velocity of point Q with respect to the person on the ground. This is very important, I am repeating. If we ask the observer on the ground, what is the velocity of point Q with respect to you? The observer will say, we have to differentiate this ROQ vector with respect to the ground frame of reference. Only then that will be the velocity, the derivative of ROQ vector with respect to the ground frame of reference. That will be the velocity of point Q with respect to the ground frame of reference. Same is the case with point P. The velocity of point P with respect to the ground frame of reference will be the derivative of ROP vector with respect to the ground frame. So this differentiation that we have to perform in order to find the velocity of point P or point Q, that differentiation is to be found with respect to the ground frame of reference. Okay, so it means we will write here differentiating with respect to differentiating, we have to differentiate it, differentiating in frame. If we perform the differentiating in frame, in ground frame of reference, we represent like this. Differentiating in ground frame of reference, we will get derivative of ROQ vector, ROQ vector. So derivative, we put a dot over it, will be equal to derivative of ROP vector plus derivative of RPQ vector. Okay, we call this as equation 2. Now see, as far as derivative of ROQ vector is concerned, with respect to the ground frame of reference, it is simply velocity of point Q as measured from the ground frame of reference. Okay, this derivative gives us velocity of point Q with respect to the ground frame of reference will be equal to, now derivative of ROP vector with respect to differentiation in ground frame of reference will give us velocity of point P, and this velocity of point P is measured in the ground frame by observer, which is in the ground frame of reference, plus derivative of plus R PQ vector and the derivative of R PQ vector. But be careful about this R PQ vector dot. We cannot write this R PQ. See, this is the derivative of R PQ vector. We cannot write this as this is VPQ. This is velocity of Q with respect to P. No. Again, I am repeating, RPQ is the position of point Q as measured from point P. Okay, RPQ gives us the position of point Q as measured from point P, because we are drawing the radius vector not from the ground. We are drawing this radius vector from point P, and point P itself belongs to the rigid body. So as far as this RPQ is concerned, RPQ is the position of point Q as measured from point P. Now, when you are differentiating this RPQ vector, you are differentiating this RPQ vector with respect to the frame of reference, with respect to the ground frame of reference. Okay, but this RPQ vector is not drawn in the ground frame of reference. It is drawn in the rigid body frame of reference. That is, I mean to say, we have actually these points P and Q. Point P and Q are actually the parts of some rigid body. Okay, we have some rigid body here. These points P and Q are the points of the rigid body. Okay, so this vector RPQ is not drawn in the ground frame of reference, it is drawn in the rigid body frame of reference, which we represent essentially by beta. Now, when we are performing the differentiation of RPQ vector with respect to ground, this differentiation will not be equal to the velocity VPQ, because RPQ differentiation of RPQ, we have to be very careful about this definition. RPQ vector does not belong to the ground frame of reference. This vector belongs to the rigid body frame of reference. Now, if we differentiate this RPQ with respect, if we take the differentiation with respect to the rigid body frame of reference, only then it will be velocity of point Q with respect to it will be velocity of point Q with respect to point P. Okay, the differentiation has to be done in the ground frame of reference, but we are doing differentiation with the differentiation is to be done with respect to the body frame of reference, but here we are doing differentiation with respect to the ground frame of reference. So we will keep this RPQ as such, and we will write this as, this is our equation 3. Okay, now let's try to solve this RPQ vector. As far as this RPQ vector is concerned, this RPQ vector we can write as, this RPQ vector we can write as, this RPQ vector is equal to, can we write this as, this is RPQ vector, can we write this as, this is magnitude of RPQ. Okay, magnitude of RPQ, and uh, this is the magnitude, and we write its direction in the form of a unit vector drawn from point P to point Q. That is, if we draw the unit vector from point P to point Q, if we draw the unit vector from point P to point Q, and we say this unit vector is, say for example U cap. Okay, therefore as far as the value of this So this RPQ vector we can write in terms of its magnitude, this is RPQ, and we write a unit vector drawn in the direction of from P to Q. So now we have the unit vector drawn from point P to point Q. Now if we look at this unit vector that we have drawn from point P to point Q, let me clear some space here. So it means we can further write this as, this unit vector we have drawn from P to Q. So if we define our, if we take an axis parallel to our, if we take an axis parallel to our x-axis, if we draw an axis parallel to our x-axis, and we draw one more axis parallel to our y-axis, so we say that this is our y-axis and this is our x-axis. Okay, by drawing an axis, by drawing a vector parallel to itself, the properties of the vector do not change. Therefore this line, this x-axis and this x, they are parallel. Therefore this angle, this angle, this is the angle that PQ subtends with x-axis. Therefore this angle of theta t has to be equal to this angle of theta t. This is, this we can say, this is the angle that this x PQ is subtending this angle with theta t. How much? Just produce this PQ backwards. You produce this PQ back, produce this PQ back. Okay, if we produce this back, so how much angle is PQ subtending with x-axis? That is this. Okay, that is theta t. Theta t. Since this axis and this axis are parallel, therefore this angle has to be equal to theta t. Don't get disturbed by here theta t is very, very large. This is not big. Theta t is here. Okay, so it means as far as this theta t is concerned, now we can write this unit vector drawn from P to Q. We can write this unit vector as, this unit vector can now be written as, u can be resolved as its unit vector, its vector along x-axis, its component along x-axis will be u cos theta. Magnitude is 1, that will be cos of theta t. We can simply write this as cos theta. Its cos theta along x-axis, that's I cap, and its component along y-axis will be u sine theta. Magnitude is 1, that will be sine theta, that will be sine theta j cap. Okay, therefore we can write this as, this is RPQ. This is RPQ. We are first writing not RPQ dot. We are writing first, trying to understand what is this RPQ. Therefore, this RPQ we can write. This is RPQ multiplied by the unit vector u cap, that can be written as cos theta I cap plus sin theta j cap plus sin theta j cap. Okay, plus sin theta j cap. Now we have to take derivative of this rpq, and this derivative we have been taking in which frame of reference? In ground frame of, with respect to the ground. Now we have expressed this rpq in terms of angle theta. Angle theta is the theta which has been measured with respect to the ground frame of reference. As far as I cap and j caps are concerned, they are the unit vectors in the direction of x-axis and y-axis, which is the frame of reference of our ground frame of reference. So somehow this RPQ we have expressed in terms of those parameters which are defined with respect to the ground frame of reference. Therefore, we can write this as, if we take the derivative of this RPQ now with respect to the ground frame of reference, the derivative of RPQ with respect to the ground frame of reference will be, this will be equal RPQ magnitude, its magnitude is RPQ, differentiation of cos theta is minus sine theta, that's minus sine theta, it's minus sine theta I cap plus, or we have to take two things here. First will be differentiation of cos theta is minus sine theta. Okay, then derivative of this theta, because when you write differentiation of sine theta, it is cos theta into derivative of theta. So differentiation of cos theta is minus sine theta multiplied by d by d theta of d by dt of d by dt of this angle, d by dt of theta. Okay, I cap plus differentiation of sine theta is cos theta and derivative of angle, that is d theta by dt, d theta by dt j cap. Okay, this is the derivative. We can further write this as, this can further be written as, this can further be written as rpq dot, let me rub here, rpq dot can now be therefore written as, we can write it as rpq vector, the derivative of rpq vector can be written as magnitude rpq multiplied by, this is minus sine theta I cap, this is minus sine theta I cap plus d theta by we can take out plus cos theta j cap. Okay, now as far as this d theta by dt is concerned, d theta by dt is common everywhere, we can take it out, and d theta by dt in can be written as theta dot. Okay, we are writing like we write d by dt of r, it's written as r dot, we put a dot simply over it for simplification. Similarly, d theta by dt is written as theta dot. Now as far as this theta dot is concerned, what is this theta dot? Theta dot is the rate of change of angle of this vector rpq. Okay, and this theta dot we call as, this is called, this is called angular velocity of, this is called angular velocity of, this is called angular velocity of vector rpq. This is angular velocity of vector, this is angular velocity of vector rpq. Okay, it's like this. Okay, so rate of change of angle, angle of what? Angle subtended by this rpq vector with x-axis, this is called angular velocity of rpq. Therefore we can simplify it, we can further modify it in terms of, in vectorial form. See, there is one more way of writing this. We can further write this as, this is the vectorial form of writing it, rpq dot. Rpq dot can further be written as, rpq dot is further written as, this is equal to, this is the way of writing it, it's written as, very important, it's written as rpq. See, here we are doing a little simplification, it's written as rpq theta dot, this theta dot is taken here, this is rpq multiplied by theta dot, and we put k cap with it, a unit vector drawn along z axis. Okay, and cross with, its cross product with cos theta I cap, cos theta I cap plus plus sine theta j cap plus sine theta j cap. Why we are doing it? Because it simplifies our equation. Look here. If you look, we have why we have written it in this form and how these two forms are equivalent. The reason to this is we write I cap, j cap, and k cap. Okay. Now, first of all, see this. You have r p q theta dot. You write this as r p q theta dot multiplied by cos theta, r p q theta dot into cos theta. Then you have k cross I. When you write k cross I, you are going in cyclic form. K cross I is equal to j cap. Okay, it is. So you got the first expression as r p q theta dot cos theta j cap. That is this. That is our this expression, isn't it? This is r p q theta dot cos theta j cap. Okay. Then you take the second multiplication. This is r p q. This is r p q theta dot into sine theta into sine theta. Then we have k cross j. When we take k cross j, you are coming in a cyclic form. It's equal to minus I. So it is minus I cap, which is your first expression here. Okay, rpq theta dot minus sine theta I cap. Okay, so this is the simplest way of writing. Writing an equation in this vectorial form is easy. Okay, so it has lots of it simplifies our calculations later on. That's why we are writing it in this form. This equation we have written in this form, rpq vector dot. If you see here, this equation can further be simplified here. This is rpq vector, derivative of rpq vector is equal to, this is rpq magnitude, okay, and cos theta I cap plus sine theta j cap. That is your unit vector u cap. If you see, you had already taken, when you resolved this u cap, it was cos theta I cap plus sine theta j cap. Therefore, this cos theta I cap plus sine theta j cap, this is what? This is our unit vector u. Therefore, we can simplify this equation as, this is rpq theta dot k cap cross unit vector in the direction from p to q. That can further be written as, okay, can we write this as theta dot is the angular velocity of point line vector pq, theta cross theta dot k cap cross, can we write this as, this is can be written as rpq u cap. Okay, that can further be written as theta dot k cap. This is rpq, this is magnitude of rpq vector, this is the direction of it. Therefore, this becomes vector rpq. This is vector rpq. Okay, therefore the final expression that we have in hand is, the final expression, very very important expression that we have in hand, the derivative of rpq vector, the derivative of rpq vector. Rpq is a vector which is drawn in the rigid body, and its derivative we are taking with respect to the ground. Okay, derivative of 2 points of the rigid body with respect to the ground is equal to angular velocity of theta dot k cap, angular velocity of the vector pq, and its cross product with rpq vector. This identity is very very important. Okay, we call this as our equation 4. Now return back to our equation 3. Equation 3 was velocity of point q was equal to velocity of point p as measured from the ground frame of reference plus r pq vector, derivative of r pq vector from the ground. Therefore, what you can write? You can write velocity of point q is equal to velocity of point p plus angular velocity of vector pq cross rpq. Okay, this expression is very very important expression for us. It gives us the expression of the velocity between it. This expression gives us the relationship between the velocity of 2 points of the same rigid body as measured from the ground frame of reference. Now look, in your lower classes, you had the rigid body in the form of a car. Like you would say that a car is translating. A car is translating, okay? Like we say in your lower classes, you had questions like the translation of a car. You were saying that a car is translating along x-axis, okay? A car is translating along x-axis with velocity 3 meter per second, say for example. And you were saying that the velocity, if you locate 2 points on the car, point B and point O, at that time you were saying that you were never saying that there is a difference between the velocity of point A and the velocity of point B. In fact, you were saying that all the points of the car, which is actually the fact, all the points of the car are moving with a velocity of 3 meter per second. The point A is having velocity 3 meter per second. Point B is also having velocity 3 meter per second. You know why? The reason for it. The reason for it is if you draw the vector between 2 points A and B, at all the instants of time, this vector AB, as long as the car is translating, the vector AB is also translating in the same direction. The vector AB does not rotate, its angle does not change. That is, if the car neither moves in this direction nor goes in this direction, as long as the car is translating, the vector AB remains constant. As the vector AB remains constant, its angle with respect to the x-axis does not change. Therefore, its angular velocity is always equal to 0. So when you say angular velocity is equal to 0 every time, you substitute theta dot equal to 0. Therefore, you will get velocity of point Q becomes equal to the velocity of the point P. The 2 points have the same velocity. So the 2 points of a rigid body have the same velocity only and only when the rigid body does not have the angular motion. When the body does have angular motion, then the 2 points have different velocities. Are you getting me? So let's now try to apply this equation to solve few questions of the rigid body. That will clear some of our confusions as well as consolidate our concepts. Thank you very much.